Welcome to my lecture on cold atoms. Today I will discuss evaporative cooling, which is our key method to reach the quantum degenerate regime in many experiments. After introducing the basic idea, I will present a model to describe the cooling process based on the repeated steps of evaporation. Finally, I will discuss how one can implement evaporative cooling in real experiments utilizing magnetic or optical atom traps. Let's start with a gas of trapped atoms in thermal equilibrium. Now we apply an energy cut. That means we remove all atoms with energies exceeding a certain threshold. This obviously results in a non-thermal distribution. Now we wait some time without applying the energy cut so that many elastic collisions can take place and re-establish thermal equilibrium. The total energy does not change in this rethermalization process, but the energy distribution again becomes a thermal one. This makes some energetic atoms reappear and, most importantly, produces more atoms at low energies. Now we can repeat the procedure. We again apply an energy cut, and this time we can lower the threshold a bit, since the sample is getting colder. We let the sample rethermalize and we repeat everything many times. At the end we get many atoms at low energies. This is real phase-space cooling, which we need in many experiments. In our model, we consider discrete steps of energy cuts and rethermalization. In reality, this is a continuous process in which energetic atoms are steadily removed from the trap. The gas continuously tends to reach thermal equilibrium, steadily producing and evaporating energetic atoms. But our model captures the essential physics very well and provides us with a quantitative description of the cooling process, as we will see on the next slides. Let us start with the energy distribution of atoms in a harmonic trap, as discussed in detail in one of my earlier lectures. Here we restrict ourselves to harmonic traps, but the generalization to other potentials is rather straightforward. The mean energy per particle in a 3D harmonic potential, as is well known from the equipartition theorem, is 3 kBt, where kB is the Boltzmann constant and T the temperature. We see that the distribution is rather broad, and we have quite some atoms with high energies. Now we apply the evaporation cut, in our example at 5 times the thermal energy. We define a truncation parameter eta, which is the energy threshold relative to the thermal energy kBt. And we switch off the cut and let the sample rethermalize. The rethermalization process preserves the atom number and the total energy, which leads us to a new thermal distribution with a temperature T1 lower than the initial temperature T0. And we have more atoms at low energy. This means increase in the phase-space density, a step of phase-space cooling. Now let's have a look at the corresponding equations. Here is the initial distribution of N0 atoms at a temperature T0. The gas has a total energy E0 equals 3 times N0 times Kb times T0. Integrating over the truncated distribution gives us the new number N1 and new energy E1 after the cut. Relative to the initial number N0 and energy E0, this can be expressed as functions of the truncation parameter, which we see here. The new temperature T1 after rethermalization can be easily calculated from E1, and we can express the relative change of the temperature from the relative changes of energy and atom number. Now we know the new thermal distribution, which we have already seen on the slide before. What does it mean for the phase space density? Recall the expression for the peak phase space density from our earlier lecture. In a harmonic trap it scales as n over t cubed. And now it is straightforward to calculate the relative change in phase space density that we obtain in one evaporation step. Let us consider a numerical example, assuming a value of the truncation parameter of eta equals 5. Our equations tell us that the number of atoms is reduced to about 88% of its initial value, while the temperature goes down to about 84%. For the phase space density, this means an increase by roughly a factor of 1.5, which is quite substantial. Our gain is an increase in phase space density, but the price to pay for it is a loss of atoms. This leads us to a question which is very important for the experiments. How can we optimize the gain to loss ratio? Just note that a real experiment relies on many repeated steps and we want to optimize the whole process. To characterize the evaporation efficiency, we introduce a corresponding parameter xi as defined here. For a single evaporation step, we assume that the gain in phase space density is related to the decrease of the number by a power law, with the exponent being minus xi. This efficiency parameter is often expressed as the logarithmic gain in phase space density over the logarithmic decrease of the particle number. For a sequence of repeated evaporation steps with efficiency xi, one can say that by losing one order of magnitude in particle number, one gains xi orders of magnitude in phase space density. This graph shows what our model predicts for the efficiency parameter xi as a function of the truncation parameter eta for the ideal case that there are no other losses apart from evaporation. One sees that in this ideal but somewhat unrealistic case, the efficiency has no limit. In reality, we have additional losses, like from rest gas collisions, no vacuum is perfect, from inelastic two-body collisions between the trapped atoms, or from molecule formation in three-body collisions. And here is what we get when we add additional losses to our model. You see two curves, one with 1% and the other one with 3% of additional losses per evaporation step. These losses do not contribute to the cooling process and thus limit the efficiency. For 1% we get a maximum efficiency of a bit more than chi equals 3 for a truncation parameter somewhat below 7. For 3% additional losses, the cooling further loses efficiency and the optimum is lower. The numbers you see here are very realistic for an experiment, where one reaches typical values of 2.5 to 3 for the evaporation efficiency parameter. Now let us consider a sequence of many evaporation steps. Here is what we get for the phase space density if we repeat energy cut and rethermalization again and again. Here we keep the energy threshold for evaporation at a constant value. The truncation parameter increases relative to the decreasing temperature, and by evaporating less and less atoms, the process slows down. This way of cooling with a constant energy threshold is called plane evaporation, and in an experiment it typically happens right after loading an optical dipole trap from a magneto-optical trap. Our example here assumes an initial truncation parameter of eta equals 7. The process can be made much more effective if the energy cut is adapted to the decreasing temperature so that eta stays at a constant value. Here in our example, eta equals 7. This way of cooling is called forced evaporation, and this is what we usually need in an experiment for achieving a large gain in phase space density. To model a realistic experiment, let us also add some additional loss, let's say 1%. While plane evaporation stops to produce higher phase space density at a certain point, here after about 30 cycles, forced evaporation keeps going and is just a little less efficient. In the latter case, with a constant truncation parameter, we can maintain conditions for optimum efficiency. Let's plot the results of our model calculation for forced evaporation in a different way. We show the gain in phase space density as a function of the relative atom number, both on a logarithmic scale. Such a double log plot is commonly used in our field, and you find it in many papers on evaporative cooling, as the slope directly shows the efficiency. In our model calculation, we obtain a value for Xi of about 3. And here are some results from an experiment on evaporative cooling of cesium atoms from our early work on the optimized production of a cesium Bose-Einstein condensate, published in 2004. The final cooling stage starts with 10 to the 7 atoms and ends with 10 to the 6 atoms. With an efficiency of about 3, see the red line, we lose 1 order of magnitude in the atom number and gain 3 orders in magnitude in phase space density until we finally reach BEC. Let's now have a closer look at the behavior of all the relevant quantities in the evaporation process. As we have discussed, the scaling of the phase space density ρ with the atom number n defines the evaporation efficiency Xi. Now we know from my earlier lecture on the classical gas in the harmonic trap how the temperature T scales with n and ρ. And we know how the number density n in the trap center scales with n and T. Moreover, as I will discuss a bit later, the rate of elastic collision in the trap is proportional to n over T. Finally, we can express all relevant quantities in powers of n, with exponents determined by Xi. We see that the number density goes up in the evaporation if Xi is larger than 1. Sounds quite counterintuitive that the number density can increase when particles are lost, but this is a result of cooling in a harmonic trap. For Xi exceeding 2, even the collision rate goes up. With progressing evaporative cooling, the process gets faster and faster, which we call runaway evaporation. This scaling of the relative quantities with the atom number n in the forced evaporation process can again be illustrated in a double log plot. We show the behavior for an order of magnitude decrease of n. For our example of Xi equals 3, the phase space density goes up by 3 orders of magnitude, while the temperature goes down by 4/3 orders of magnitude. The number density goes up by 1 order of magnitude, and the collision rate increases by 1/3 order of magnitude. This is very efficient evaporative cooling. We really gain a lot by sacrificing just a factor of 10 in the atom number. Okay, we have seen that evaporative cooling requires thermalization by elastic collisions. Now, let's stay within our model of repeated evaporation steps and consider an important question. How many collisions are needed for one such evaporation step? To answer this question, let's look at the relative atom number decrease in one step as a function of the truncation parameter eta, as discussed on slide 12. The relative loss delta n over n corresponds to the probability for an atom to leave the trap. Let's call it P evaporation. But how many elastic collisions does an atom experience on an average before it leaves the trap? This quantity, let's call it n evaporation, will of course depend sensitively on the value of the truncation parameter eta. For the relevant range of eta, I can present a simple approximation which I have checked by a Monte Carlo simulation. N evaporation is approximately given by 4 times e to the power of eta divided by eta squared. And now we can put things together to derive the mean number of elastic collisions per atom in one evaporation step. This quantity results as a product of the probability for an atom to be evaporated and the number of elastic collisions needed for an evaporation step. P evaporation times N evaporation. We finally arrive at the simple expression for the mean number of elastic collisions for an atom in one evaporation step, 2 plus 4 over eta, neglecting higher order terms in 1 over eta. Let's now consider realistic numbers, assuming eta equals 7. The probability for an atom to leave the trap, corresponding to the relative loss, is then about 3%, with about 90 collisions that an atom experiences on an average before leaving the trap. We finally arrive at 2.6 collisions per atom for one evaporation step. Now we know how many collisions we need for one evaporation step. But how many collisions do we need for gaining, let's say, 1 order of magnitude in phase space density? On slide 20, we have already seen that for eta equals 7, we need about 18 evaporation steps. This tells us that we need approximately 50 elastic collisions for gaining 1 order of magnitude in phase space density. Let me note that in practice, when things are not ideal, the number may be significantly larger. Let's now turn our attention to our main enemy, inelastic collisions. While elastic collisions are good for the evaporation process, inelastic collisions are bad collisions. The latter lead to additional trap losses, which make the cooling process less efficient. Note that in a single elastic collision between 2 atoms, the large energy release kicks both atoms out of the trap. To estimate the required ratio of good to bad collisions, we stay with our example of eta equals 7. We have seen when discussing slide 20 that efficient evaporation permits something like an additional loss of 1% in a single evaporation step. That is, the number of inelastic collisions should stay below 0.5% of the total number of atoms. We also know that one evaporation step needs about 2.6 elastic collisions. This together gives us the required ratio of good to bad collisions, for which we obtain the large number of 500. This condition sets a stringent requirement for the scattering properties in a quantum gas. This tells us that to achieve efficient evaporative cooling, we have to understand, control, and optimize these scattering properties very well. Finally, we have to discuss the time scale for evaporative cooling. And this is set by the rate at which elastic scattering takes place in the trapped sample. The elastic scattering rate per atom in a trapped sample can be calculated as a product of 3 factors. First, the mean sample average number density n bar, which for a Gaussian-shaped cloud is the peak density divided by square root of 8. Second, the scattering cross-section sigma, which I will discuss in a minute. And third, the mean relative velocity, which in the thermal sample is obtained by the expression shown here. From the first and the third factor, we see how the elastic scattering rate scales with number density and temperature. Or considering the harmonic trap with the total number of atoms capital N and the temperature T. The elastic scattering rate is proportional to N over T, and we have used this scaling already before on slide 23 when we discussed the evaporation efficiency. The remaining factor is the elastic scattering cross-section sigma, Quantum mechanical scattering theory tells us that for identical bosons in the low energy limit, sigma is given by 8 pi times a squared, where a is the so-called S-wave scattering length. The latter is the length scale that characterizes the quantum mechanical interaction. To give an example, for rubidium-87, the scattering length has a value of slightly more than 5 nanometers. This is a typical value for the interaction between ultra-cold atoms. But depending on resonance properties, it can be much smaller or much larger. Finally, I would like to note that an elastic scattering rate on the order of 100 per second is typical for evaporative cooling experiments. A sufficiently high elastic collision rate is another requirement which is not always easy to reach in real experiments. The typical timescale for an evaporative cooling process with large gain in phase space density is something like 10 seconds, sometimes less, sometimes more, depending on the atomic species, the particular trapping scheme, and the experimental parameters. Evaporative cooling can be very powerful, but its implementation needs very careful choices of the experimental conditions and procedures. And now let's go to the lab. The question is, how can we implement evaporative cooling in a real experiment? Well, the answer depends on the particular trapping scheme. Let's first consider a magnetic trap. Here I show the magnetic potentials of the lowest hyperfine state at the example of a rubidium-87 atom. As discussed in my lecture on magnetic traps, the atoms are trapped in the low field seeking state with magnetic quantum number mf equals -1. The trick now is to apply a radio frequency. The radio frequency is very selective and couples the Zeeman sublevels at a very well-defined three-dimensional surface in the trap. If an atom reaches this surface, it has a high probability to get transferred to another sublevel where the atoms are untrapped and they are removed from the trap. This defines very precisely the energy threshold for evaporation and thus, in relation to the temperature, the truncation parameter eta. Because of the sharp cut into the energy distribution, we sometimes call it a radio frequency knife. Radio frequency induced evaporation is easy to implement, very efficient and well controllable. Forced evaporation can be achieved by sweeping the radio frequency according to the decreasing temperature. In an optical dipole trap, the trap depth can be reduced by simply ramping down the laser power. But something is different to the scenario discussed before. A reduction of the laser power also reduces the trap frequency omega, and omega is proportional to the square root of the power p. In our simple model presented before, we had assumed constant omega. With varying omega, the scaling laws for density, phase space density and collision rate need to be modified, which however is not very difficult. As an important consequence, the decompression of the cloud with decreasing omega makes it very hard to achieve runaway conditions. For gaining several orders of magnitude in the evaporation process, one has to play additional tricks, like dynamically reducing the laser beam diameter by a zoom lens. I will present another powerful trick in a minute, but let's first discuss another important effect, the role of gravity. Gravity adds a constant slope to the trapping potential in the vertical direction. For a magnetic trap with radio frequency applied, the situation now looks like this, and for an optical trap like this. We see two effects. First, the trap depth is reduced. This can sometimes even be helpful to implement efficient evaporation in optical traps. The second effect is a reduction of the evaporation surface. atoms are no longer removed in all directions, but they can only leave the trap through a hole at the bottom. This reduction of the evaporation surface can compromise the efficiency substantially, since atoms may suffer from inelastic collisions before they find the hole to escape. The effect of gravity has to be considered in any shallow trap used for evaporation, in particular if one works with a heavy atomic species. Let me note, however, that in optical traps, the effect of gravity can be compensated by magnetic levitation techniques, that is, by applying a magnetic gradient in vertical direction. And this is something we routinely do in our labs. Finally, let me present an interesting and nice trick to implement a large evaporation step. We call it the Dimple trick, and in some cases it can be really very helpful. In the first step, we prepare many atoms in a large volume trap. This can be an optical trap or a magnetic trap. This large sample then serves us as a reservoir with temperature T. The next step is to add a narrow potential well to the center, in practice realized with a tightly focused red-tuned laser beam, the power of which is ramped up slowly. This dimple is then filled by elastic collisions establishing thermal equilibrium. And now comes the key point. While the temperature stays nearly unchanged, as it is determined by the large reservoir, the locally increased potential depth leads to an enhancement, which can be understood by simply looking at the Boltzmann factor. In the final step, the reservoir trap is turned off, which removes all reservoir atoms. What remains is the narrow dimple potential, which contains a sample that is very dense and has a substantially increased phase space density. This is a very powerful trick, which works like one big evaporation step and which nowadays is used in many experiments. In Innsbruck, it was an essential step in our first experiment that reached BEC of cesium atoms. And now I hope you are all well prepared for your own evaporative cooling experiments. I wish you success and fun in the laboratory.